But now we see it here on the right-hand side. We have different type of exposures here. This is actually, wait, how does that work? Whoa, okay. We have different types of assets, and this is just actual reported data, reverse repos as we have seen before, but there's also just direct lending that is unsecured, or even equity exposures or short-term money placements. And all of them just are exposures that banks have and they need for, I don't know if they need for what they exactly needed, but sometimes just like for different types of maturities, and they like to use them. But now if we think of a shock that would propagate through the system, the question for us is, well, how? Because it's surely not the same for all of these layers. And that's a big problem to know. So that is, how can we quantify effects of that? So just because we have that, we have a weighted network that is even directed, doesn't tell us anything of how would a shock actually go from one thing to another. Now let me go quickly to the graph here. So what we have here is a multi-layer network graph that we will now later nest into a network regression. Is each layer here is one asset type, and each of the nodes here is one financial institution. The center institutions here in black are the big 6 banks in Canada. They are reporting that report for OSFI, that's at EBT2A. And all the outer circles are like financial institutions, either in red in Canada or blue US and so on. And you see these middle ones are connected, saying that if there's something happening on this market and the financial institution here, the center one, is getting a problem, well, it will also have a problem in all the other layers. And then it can potentially spread in one layer, go back to the next layer, and spread there too. And that's the question to how do we actually reconcile all of that together. So here's the research question: how do we quantify contagion in that context? And then for us, more importantly, then how much do the different systemic risk channels, as we just defined them in the first slide, contribute to the transmission of the shocks between banks? We use the method here. It was first we estimate the correlation of time series. We use like this correlation as some type of proxy of systemic risk, because again, correlation of the stress can kind of be seen like that. And then we identify the actual spillovers by the fact that we observe the networks, as we've seen in the multi-layer network, and that can kind of be seen as a quality constraint for structured VAR models. Okay, so what is the model? I actually forgot how much time I have. Okay, all right, then I will focus a bit on that and skip some other slides. So here, first, the model is quite important. We have contemporaneous dependencies. What does that mean? That, well, usually we often have contemporaneous dependencies, but here it's important we have a time series observation that is only dependent on itself. So now assume we have a time series observation, vector YT, that is a vector which includes all banks and all financial institutions of our system. And we assume there's only 2 types of sources that can lead to variations in this vector. There's the endogenous part and the exogenous part. And now that we split this one by basically saying, okay, there's the YT, which is dependent on the endogenous side and on the exogenous side. And this one is sometimes seen as shocks here from the macro literature. We've seen it also with the impulse response just today. But what is the endogenous side here? Well, it means that YT is not just on the left-hand side, but it's also on the right-hand side. And that's a bit confusing as such. Why don't we just solve it? Well, this is a vector. This is a vector, and this one is our network matrix, and this one is our sensitivity. So if we look at how we define it, this is the number of banks, M, that includes all the vector of observables. We will use a proxy for their financial health by using the capital ratio of the banks. We have the observed zero-diagonal network matrices, so some type of agency matrices that I then just put in here. And then we will have for each of these assets, asset layers, we will have one sensitivity parameter. That's the network sensitivity parameter beta. And then lastly, we have one thing that would kind of lead from the systematic risk part, that is how these shocks actually impact the system. So how do they actually distribute over the banks when a shock comes and enters the system? And that's the exogenous part here, that is X times epsilon t. We have basically, in statistics terms, just a dimension reducing matrix that's just the rest of the balance sheet of the banks. And now we have an exogenous shock vector that can be shocks to mortgages or housing or anything that is bad for the banking system as such. So this one here is, now it just looks like a standard regression approach, is actually just derived from the balance sheet. So it's just nothing else than a balance sheet idea, and we just get some disturbance terms on the right-hand side. But how do we solve that one? Well, simply by putting YT on the left-hand side. And now this may look familiar to most of you here, but if we put it to the left-hand side, now we have basically just this one bracket here where we have the identity minus the sum of the sensitivities times the adjacency matrix. We take the inverse of that, which will lead to a Leontief inverse, which you're probably all familiar with. And then we have this multiplied by the impact matrix plus the shocks itself. And this we will have here, and this is quite interesting what that is, because that's just the infinite game of the network matrices played. Why is this a weird regression as such? Because this is observable, shocks are not. Shocks don't exist. They don't exist as observations. They're just by definition not there. So how do we get the parameters beta from this one? Well, we have a covariance matrix. And this is it. We take the covariance matrix of YT and look at what the covariance matrix has. We can estimate this covariance matrix as this one. That will be just an n squared matrix, which is symmetric, so we don't have like the full matrix, only the upper triangular as information. But this one then only contains a couple of information that is basically the covariance matrix of the shock vector and the sensitivities that is unknown to us. Now, since we only have a smaller set of parameters we have to do, we can actually estimate this one from the covariance matrix estimation. So we estimate the covariance matrix first, and then we identify the betas and the covariance matrix of the shocks itself. Okay. I will now quickly go through the application here because that was the original motivation, and we kind of want to also get insights from the data here. This data is monthly data. It's regulatory data for Canadian banks. That is going from 2007 to today. We have 6 big banks and 4 smaller banks in here. We had to drop one of the banks because they stopped reporting. And the data that we do not have, we had to interpolate it, and some of the returns we had to extrapolate it because they don't go and date back so far. But we have sufficient information to make the explanation also useful. We have 3 types of channels for Contagion. First is basically the interbank assets, what we saw from the multi-layer, but we also include 2 more types of Contagion. That is, first of all, investor sentiment. That is, if one investor feels like the bank is not doing so well because another bank is not doing so well, they may decrease their funding to that. So that will also lead to more funding pressure to banks, and we'll go down. Further, we will use price-mediated effects. You may know that under the term fire sales, but fire sales only is actually a problem if there's actually a liquidity squeeze. We also include them in a way that sometimes they can lead to positive effects. If one bank buys a lot of assets, they may increase the mark-to-market asset exposure for another bank. And then the exogenous impacts are usually just mortgage loans, business loan securities, and the funding side as such. Here's the banking system, just summarized in one number, like how much stress was there actually. This is just a small index for the 3-month difference of the aggregate capital ratio of the banking sector in Canada. And actually we don't, that's a bit of a bummer compared to the US, like for us and analyzing it, because there's not a lot, because even if you look at the great financial crisis, yes, there was a lot of variation, but actually it was kind of okay for Canada. So we probably do not observe so much contagion and so much stress as in the US system. But we have some drops here in 2018 with Home Trust, and those we still want to see what comes up. That's the main graph. Well, we have the system variance, and we now take the variance of the system for the 10 banks we just had in here and decompose this by channel. So we have here first in black the total variance that goes up quickly before the financial crisis, but then lowers down with the Basel III requirements kicking in. So basically the banks are starting to be less volatile, but on the other hand have just maybe more similar. And then we decompose this one into first Contagion, that is the yellow line here, as we see that basically follows the same dynamic here and is mostly responsible for this part. But we also have the idiosyncratic part, so actually there's quite some individualism still between banks. So it's still like the risk may emerge from single banks still as such. And common exposure then, and this is the interesting part, was actually not so important to that, but just after the COVID period just started to level up a little bit because like the risks emerging at the time then are more common to the banks, in particular with increasing interest rates. So how do we decompose the contagion here? Well, we just look in the different network sensitivities we had over time, and we look at how much they contributed to this contagion here. And I see the color choice may not have been super perfect, but this is just the, in black, we see the overall contagion components over time from 2007. And you see that each of these colored areas relates to one of those layers we had, plus the two added contagion ideas here. And we see that most of the time that the contagion level is around like 40% here, whereas then just at more stressful times, we see that in particular the market-based, so the investor-based contagion is kicking more in, whereas like the price media contagion is adding to the rest. That is obviously for, if there's more market movements, it's more likely that they contribute more to the results. Interesting here, the model picks up low spillovers at the end of the sample. This one, I actually don't know how much time, I'd rather have questions, so I skip this one. So that's the conclusion. I just said everything, so I'd rather take questions. Thank you.
Great. Thank you. Thank you very much for that.
So your informal equation at the start, systemic risk, contagion times systematic. So where do you see that in the regression formula? I could not find.
That's basically this one. If you take this one here, and that's like the vector of all banks, then this part is the endogeneity part that will lead to the contagion. This one is your impact matrix, so that's the common exposure. And this one here is your shock from the outside that may actually be potentially also the idiosyncratic risk.
So why is it not contagion times systematic times idiosyncratic? So how do you have the idiosyncratic plus?
I think that's what we wrote, no?
I think you had systematic plus idiosyncratic.
Yeah, so exactly. So these risks come from the outside, but both can be multiplied, right? Because
Thank you.
Do you have any identification issue in the model?
That's a very good question. Technically, yes, if the networks are multicollinear and they exhibit the exact same patterns, then we cannot identify any effects there. But since those are weighted networks, and it's very unlikely that it's collinear in that sense. So empirically we don't find that. In simulations, we found that a couple of times, yes.
But you don't have problem parameter. You don't have to make parameter restriction. So you have enough parameter to.
So we have to limit the number of shocks.
Right.
That's basically this one here. We have to limit. That's why we have a dimension reducing matrix. We have to limit that because we don't have so much parameter space here. We can technically increase the covariance matrix by a lot more, and then we can include more shocks. But the problem becomes then that it's near to like the high dimensionality kicks in, and we can't actually estimate it anymore in a meaningful manner. Yeah.
Thanks.
Thank you.